Good afternoon and welcome back to the second session, today's afternoon session. So both the talks are going to be online. First talk is by Professor Victor Beresnevich. He's going to talk about Borel-Cantelli Lemmas for inhomogeneous Diophantine approximations and beyond.
Can I start?
Yeah, we can start.
Okay, thank you very much. Good afternoon, good morning, if someone is joining from another time zone. So in this talk, I'm going to talk about tools rather than solutions to some kind of problems. And the tools will be basically variations of the Borel-Cantelli lemma. And the motivation for this development lies in the theory of inhomogeneous Diophantine approximation. So let me start by introducing the key problem. So what you see on this slide is a very basic fact in the metric theory of Diophantine approximations called Khintchine theorem. Was proved nearly 1,000 years ago. So you look at the set of psi approximable points, W of psi, and Khintchine proved that assuming that psi is monotonic, well, his original statement required a slightly stronger monotonicity assumption. Then this set occupies almost a whole of the unit interval. All right, so that's the set I'm talking about, and that's the statement. Of course, in the convergence case, we also have a statement. If the sum in one converges, then the set W of psi has measure 0, which is a very simple consequence of the first Borel-Cantelli lemma. So the question that was raised in 1941 by Duffin and Schaeffer was to remove the monotonicity assumption from Khintchine theorem. And they provided a counterexample to a plain removal of any conditions on psi. So they constructed a function psi, which actually was monotonic on its support, but it wasn't supported on the whole set of natural numbers. And for that function, the sum of psi was divergent while the measure of W of psi was 0. And consequently, they came up with this alternative set where they introduced coprimality of A and N and raised the following conjecture, known as the Duffin-Schaeffer conjecture. So they conjectured that whenever a modified sum, which involves phi, that's totient Euler function, whenever the sum diverges, again you have a similar statement. The measure of W dash of psi is 1. There is also another related conjecture posed by Catlin in 1976, which does not require the coprimality condition. Catlin's statement was different. So what I've given here is as an equivalent formulation published by Ramirez in 2020. And why I'm stating this form is just because it's easier to generalize to inhomogeneous case rather than what Catlin stated. And of course, we have the inclusion. W dash is always contained in W for the same function psi, and therefore the Duffin-Schaeffer conjecture implies Catlin's conjecture. In fact, Catlin conjectured and claimed in his paper that both conjectures are equivalent, but later there was a fault was found in his proof, and the two conjectures are different. Right, so there were many partial results until 2020. starting with Erdős, then Barler, Point, and One, and more recently, several papers on the so-called Duffin-Schaeffer conjecture with extra divergence, until in 2020, Kokolopoulos and Maynard proved the conjecture in full. So this is a brief history of the homogeneous case, and I will be interested in the inhomogeneous case, when you insert an inhomogeneous parameter into the set W or W psi. So you basically shift A in either of these sets by a fixed parameter. But before I go into it, let me comment a bit about the proof, the proof of this conjecture is based on, the homogeneous one. It's based on what is called Divergence Borel-Cantelli Lemma, and there are several versions of it. So here I'm stating perhaps the most general version, which requires the mildest condition on the independence of the events. So you have a probability space, a sequence of events which measures diverge, and then you ask for this condition 5, which is commonly called quasi-independence, quasi because you've got this constant C, which is allowed to be anything, and on average, or average means that you have sums, so you it's not just pairwise, but you're averaging this. Right, so the divergence Borel-Cantelli lemma basically gives you a tool for proving that mu of E infinity, the lim subset, is of positive measure. So assuming you can verify these two conditions, the measure is positive. And this is applied, of course, in the case of the Duffin-Schaeffer conjecture. And I have to say the main difficulty is to actually verify condition 5 somehow. This is where a lot of number theory lies, and a lot of sophisticated tools are used. Right, so, but this only gives you a positive measure, right? So if you're lucky enough and skillful and can get constancy arbitrarily close to 1, of course you can get full measure, but this sometimes is a difficult thing to prove. And therefore, one usually use a different tool for that, for proving that W dashed is a full measure. But before I describe that tool, let me say that one comment about condition 5, about the possibility of proving the Duffin-Schaeffer conjecture in some other way. So essentially, this is the only way how you would go about proving the conjecture. And this follows from a very simple statement that is published in a recent paper by myself and Velani. So basically, if you're considering a lim subset of intervals in 0, 1, the only way to prove its measure is positive is to find a subsequence which satisfies the conditions of the divergence Borel-Cantelli lemma. So somehow up to saving your sequence of intervals, there shouldn't be any other way, right? At least theoretically. Now let me go back onto describing how the Duffin-Schaeffer conjecture was proved, and the question I'm now going to consider is how you go from how you get full measure from just positive. Right. Okay. So of course there are various tools, and one which is quite universal and quite popular as well is to use the Lebesgue density argument. So here I stated stated it for the specific case when you would be interested in the Duffin-Schaeffer conjecture. So if you plug here A, you'll set W dash psi, and if you can verify that on W dash psi, or A in this case, restricted to any sub-intervals of 0, 1, has measure bounded below by a proportion of the measure of this interval I, then you conclude that the set has full measure. So this requires using the Borel-Cantelli Lemma stated before, requires that you, in particular in the case of Duffin-Schaeffer conjecture, restrict events En to an arbitrary interval and perform these calculations 5. And still you would need some precision. You wouldn't just need an arbitrary C, you would need something which would be a proportion of the measure of I, right? So, so this is how you can go about. I'm not going to comment on any potential technical difficulties in pursuing this approach, because no one really ever tried it. A slightly more general statement that would not require Lebesgue density is when you can bound the same quantity, the measure of A intersecting with, this time not interval, any open set. If you can show this is bounded by a decreasing function of the measure of U, so this time it doesn't have to be constant time the measure of U, measure of I in that case. Could be anything, any decreasing function tends to 0. Then again, you can make the same conclusion, but this time you're up against verifying this for an arbitrary open set, and perhaps you'll end up checking what's in the first lemma on this slide. The actual proof of the Duffin-Schaeffer conjecture, however, is based on Gallagher's 0-1 law, which was found in 1961. So what it proves that the measure of W dash psi is always 0 or 1, right? So as long as you prove it's positive, you conclude it's 1, right? And so if you put together this result of Gallagher and the Borel-Cantelli lemma I stated before, you get the following statement. So this is a theorem, right? And it's not a theorem that you would find in literature. I basically put together Gallagher's theorem and Borel-Cantelli lemma, right? So if you verify this condition 6, so this expression 5 psi over n is basically half the measure of En, right? So this condition 6 corresponds to the requirement that the sum of measures of En diverges. And then condition 7 corresponds to the quasi-independence on average requirement in the Borel-Cantelli lemma. So condition 6 and 7 would allow you to conclude, if you can verify them, would allow you to conclude that W dash of psi has positive measure, and then you apply Gallagher's 0-1 law to conclude it's actually 1, right? So this is actually what everyone is using to prove any statements around the Duffin-Schaeffer conjecture and the actual Duffin-Schaeffer conjecture. So the main question I want to ask and answer in this talk is about the existence of a similar statement in the inhomogeneous case. So why I'm not asking about the existence as 0-1 law, so let me explain this in the first place, because then you would naturally get this kind of statement. Okay, before explaining that, let me formally put forward what we mean by the inhomogeneous Duffin-Schaeffer conjecture, basically you shift the integer parameter a in the inequality that defines your set by a fixed parameter gamma, a fixed real parameter. Right? If gamma equals 0, you're back to the homogeneous case, and then the inhomogeneous Duffin-Schaeffer conjecture states that under the divergence sum condition with an 8, the Lebesgue measure of W dash gamma of psi is 1. You can also state a variant of Castlin's conjecture. So this is where you simply drop the coprimality condition, and obviously it's so in the definition at the top line, A and N are asked to be coprime. This is what it means. So here is just a pair of integers and positive, and you ask for the inequality here to have infinitely many solutions NA. So Castlin's conjecture is obviously a little weaker statement because it's about a bigger set under the same condition, and the inhomogeneous Duffin-Schaeffer conjecture would imply the inhomogeneous Castlin's conjecture. So what I already said, advertised, and will do in the next few slides is I will explain why I'm not going about simply asking about the existence of a 0-1 law, like in Gallagher's case, for the inhomogeneous approximation, but rather ask about this type of theorem, which you would obtain by combining Gallagher's result and the Borel-Cantelli lemma. Right, so I'm not going to explain the details of Gallagher's proof. I would rather explain somewhat simpler Castle's 0-1 law, which was actually a precursor of Gallagher's 0-1 law. The Castle's proved a similar statement for the set W psi, where you don't assume any coprimality. So here is a sketch proof. So you start off by forming a new set, and you take the union of W C psi, where C is a constant. It's a relatively simple fact to show that this W tilde has the same measure as W. It's proved using Lebesgue density argument. And then you proceed as follows. You pick any point in the set W tilde X. By definition, it means that this inequality, mod nx minus a less than c psi of n holds for infinitely many an, integers an. And then you multiply this inequality, let's say, by 2. So you get 2nx minus 2a, and just do these plain transformation. So you replace, so you pull out n from the first term and take 2x mod 1, right? So you will get n times 2x mod 1, and to take 2x mod 1, you just need to subtract the integer part of 2x. That's what's written here, right? And to keep it equation, I need to add that term, n times integer part 2x, that appears in here, right? And you've got that term minus 2a. So you've got another integer in here, 2a minus n, integer part of 2x is just an integer. And the right-hand side scales up by 2. And you've got this for infinitely many integer pairs. This time it's a dash n, right? So what it means that if you double x mod 1, you'll end up with a point in 2c psi of x, but by definition, this is going to be a subset of W tilde, right? So that means that W tilde of psi is invariant under the Dublin map on the unit interval, mod 1. We know this map is ergodic, and so the set W tilde of psi must be trivial. So it's measure 0 or 1. So that's basically the whole proof, up to some technical details. And I have to note that Gallagher's proof follows a similar line, but it requires some sophistication because you need to keep the cochromatic condition as you do this multiplication by 2 or anything else. And for that reason, Gallagher had to represent what would be an analog of W tilde psi is W tilde dash psi as a countable union of sets which would be invariant under these maps multiplication by a prime plus a shift by a rational. Right, but other than that, it goes basically the same line. So what's the problem with the inhomogeneous case? So if I start off with the same inequality as above, as I did for Castle's theorem, but this time I plug in a gamma, right? And multiply by 2, gamma scales up by 2 as well, as you see, right? So if you do all the same kind of transformations, you've got pretty much the same stuff, but this time, gamma changes, and that is a bit of a problem. So essentially, instead of ending up with a point in the same set, which I'm calling here a W tilde gamma of psi, so that would correspond to the inhomogeneous case, you end up with W tilde with another gamma, with a gamma which is doubled as well, right? So as you can imagine, in the Gallagher's 0-1 law, if you try to repeat the same argument, because you have to use multiplication by basically arbitrary primes, you could end up in any of the sets W tilde P gamma, where P is a prime, right? So you basically don't have the same kind of invariance. You can show something. You can show that at least one of the sets maybe has measure 0-1, but you cannot prove it individually for a particular gamma. So that is a problem that you can see. Of course, there may be other maps which are ergodic and under which W tilde gamma or any other related set is invariant, but that is an open thing, right? So I hope I explained the difficulty in using in generalizing Gallagher or even Castle's 0-1 law to the inhomogeneous case. Right. So this is just a repeat of my question. So I've got this 0-1 law, not 0-1 law. I've got this combination of the Borel-Cantelli Lemma 0 and Gallagher 0-1 law, stated as theorem. I stated before. I just repeat it here. And the question is, rather than asking for a 0-1 law, does an analog of this statement, Gallagher combined with Borel-Cantelli, hold in the inhomogeneous case? After all, this is really what we need to attack the inhomogeneous problem. I wouldn't probably ask this question if I didn't have the answer. The answer is yes. And here is a theorem. So I have to say this is a joint work with Sanjay Velani. And the statement is basically the same, absolutely the same as you've seen on the previous slide, with the exception that now you allow an arbitrary gamma, so the statement applies to the inhomogeneous case of the problem. So as I mentioned before, the proof does not use any sort of 0-1 law as before, and it follows directly from a modified version of the Borel-Cantelli lemma that I stated at the beginning. Let me just repeat that lemma again. So this is what we have. The divergence Borel-Cantelli that I've shown at the beginning of this talk. You've got the divergence sum condition, which is necessary to hope that the measure is full, and you verify this quasi-independence on average condition. Then you conclude that the measure is bounded below by the constant c to the -1 that appears in 15. I have to say that this is sharp without any additional conditions imposed on En. This is sharp, right? And I've provided here a very trivial example. I'm sure you can come up with more sophisticated examples, but if you plainly take a constant sequence of half intervals within 0-1 for each I, then obviously 14 holds, and 15 is easily seen holds with c equals 2, and the lim subset is not comma half, and so it's measure half, which is exactly 1/c, right? So if you don't put any extra conditions, this is really sharp. What is an extra condition that we added into this lemma to ensure that the measure is bigger, namely 1? So here is the statement. So in the first half of the statement, you will find so basically 16 and 17 is what you've seen already in the standard version of the divergence Borel-Cantelli lemma. So everything in the first half is what is asked in the standard divergence Borel-Cantelli lemma. And the extra conditions that we impose is this condition. I call it M1 for the purpose of this talk. So it says what it says. So you fix any finite union of the events in your sequence, right? So you fix any parameters Q1 and Q2 and take the union of the events in your sequence, take any arbitrary small delta, and then you should be able to show that A and En are effectively independent, right? So if I had equation with the one, it would mean independence. You can call it a quasi-independence, but it's really close to being independent. Right? It's also along the lines of what you would normally see in dynamical systems as a mixing condition. Again, if I had here equation and En was some kind of sequence arising from a dynamical sequence that system, then as delta tends to 0, then that would imply mixing. That's partly the choice for M. So it's a mixing type condition, right? And then if you can prove that M1 holds in addition to 16 and 17, then you conclude that the measure of the lim subset is 1. So perhaps it's not a surprising statement, and the proof is indeed relatively simple. It's different to what you will see as a proof of the standard Borel-Cantelli lemma, which uses the Cauchy-Schwarz inequality essentially. But this is what it is. and it solves the task, right? It completely solves the task of answering that question. So let me show again how what we are aiming to verify. So this is just a copy of the statement that I'm targeting to verify. So under this divergence sum condition and quasi-independence on average, I'm hoping to conclude that the measure of W dashed, it's got to be double dashed gamma, right? So the inhomogeneous one, we're hoping to conclude it's 1. Right, so if you see the first two conditions are simply embedded into that statement, so the only condition that we need to check is M1, right? So this is what is missing here, and this is what I'm hoping to verify. 19 and 20 simply verify 16 and 17 on this slide, right? And M1, this is just a repeat. I need to verify this statement. So let me make a comment at this point before I show you the proof. So A is a finite union of the sets En, which are themselves collections of intervals. Right, so you have a finite collection of intervals each time, and you take a finite union like that. So you have a finite union of intervals. So A itself can be written as a finite union of disjoint intervals, right? So if two intervals in that union 21 overlap, that they just form another interval, right? So A is a finite disjoint union of intervals, right? So so basically, when you verify 21, it's enough to assume that A itself is an interval, right? So if you can check it for every interval in place of A, then you're in business. 21 will be true as stated. Right? So I will assume A is just a closed interval, A1, A2. So how do we go about showing M1? So let me recall that En is a union of these intervals, which I will call ENA. So this union is taken over co-prime integers A, co-prime to N. And that's the intervals that appear in this union. So I want to find the measure of the intersection of En with this closed interval A1, A2, right? So basically, you can do it by counting how many intervals in this union of En have a non-empty intersection with your fixed interval, right? And then multiplying that count by the measure of a single interval ENA, which is obviously the same. It's every time it's 2 times psi of N over N. That's the length. Or at least an upper bound. It depends how you interpret this. If you interpret the unit interval as written, then 2 times psi of N over N will be an upper bound. If you take everything mod 1, then you will have equation. Anyway, so this condition, that the intersection of the closed interval A1, A2 and ENA is non-empty, is easier to write. It's an intersection of 2 intervals. So when you rewrite this condition, you'll get 2 inequalities from above and below on the integer A in here, which is the only parameter. Everything else is fixed. N is fixed, A1, A2 are fixed, gamma is fixed, psi is fixed, right? So A here is the only thing that we need to count, and it lies in this range. So it's very easy to find how many A's you've got in here. It's roughly the length of the interval, the difference of what you have on the right and what you have on the left, right? So that the difference is written here in the numerator. That's the difference. So if I wanted to count the number of a's satisfying this, that would roughly be this quantity. I'm saying roughly because you need to round it to the nearest integer and perhaps add a 1. But we are after a's which are co-prime to n. Therefore, we need to exclude all the a's which are not co-prime to n. And here we can use a very standard, for number theory at least, inclusion-exclusion argument, which is written here using mu. It's called Möbius function. So basically, mu equals -1 to the number of prime divisors of d if d is square free, and otherwise it's 0, right? So for instance, if d is a prime, the mu of d is -1. So what you have in here, this quantity in the brackets, is the number of integers a which are divisible by that prime, right? So when d equals 1, mu of d is 1, and what you have in here is just the total number of integers a in that interval. So you pick the total number of integers in that interval, then subtract for each prime d dividing n, you subtract the number of integers in that interval which are divisible by that prime. But then there may be integers which are divisible by 2 primes. You remove them twice. That comes comes back when d equals a product of 2 primes. It'll be a 1. So you add them back and so on, right? So it's really just inclusion-exclusion argument written using the Möbius function. And then you use some standard identities for the Möbius function or the function. So when you calculate this, it gives you just the measure of your interval, a1, a2, 2 times psi of n over n. That comes from this term. And the sum over d of dividing n, mu of d, n over d, just gives you the Euler function phi, right? And you have this remainder, a small remainder, which is easy to estimate, because mu of d is always bounded by 1 in absolute value. So when you take the absolute value of this remainder sum, is bounded by the divisor function of n, d of n, right? So this is eventually the bound that you get for the number of integers a co-prime to n, satisfying this condition, or equivalently such that this intersection is non-empty, right? And therefore, you have the measure estimate, as I explained. So this is the bound that we found, times the measure of a single interval. You need to multiply the measure of a single interval E and A by the Euler function. That's how many intervals you've got in the union, which forms En, and respectively, you need to divide this expression by the Euler function. So this goes, and you divide the divisor function by phi, and this is basically 1 plus little o times mod AEN, right? So you can now extract your delta. You can do it efficiently, even showing how far you need to go in terms of n to get the delta that you want in this property M1. So hopefully I explained, and this is essentially a whole proof of this statement, assuming this new version of the Borel-Cantelli lemma, which I hope you believe is true. Right. Right. So so this is basically the main part of my talk. The rest of it will be, I'll throw various other statements onto you, which arose in considering this problem. So first of all, I think I lied a bit when I said that that statement at the beginning is what the proof of the Duffin-Schaeffer conjecture relies upon. It relies upon a slightly different, a more generic, more general version of the Borel-Cantelli lemma, where the summation isn't taken from one, the summation is taken in some interval between two integers. So you need to find infinitely many of this when the sum accumulates enough of mass. It should be about a constant. This is what this expression means. And you need to be able to verify the quasi-independence on average rather than on the range 1 to n, on this reduced range, which I call here mk, nk, right? So this is what, if you look at the actual proof of the Duffin-Schaeffer conjecture, this is a statement that is used to prove the conjecture, plus Galga's 0-1 law. So if you put them together, you get this, if you like, theorem. So this is just the more general divergence Borel-Cantelli lemma. Maybe it's not so important. Obviously, using the same kind of approach as I described, you can verify a similar statement for the inhomogeneous problem, right? So the statement is very much like what we've seen before, but this time the range of summation is restricted to some finite subset, which never starts from 1. It starts from, let's say, some integer which tends to infinity. So that's embedded in this condition that the set Sk is in subset of integers greater or equal to k. And if you try to match it to what you've seen before for the homogeneous case, you would take Sk as this interval of integers mk and k for some sequences of integers mk and k that tend to infinity. Condition 26, it basically corresponds to the divergence sum condition in the Borel-Cantelli lemma, in the standard Borel-Cantelli lemma. But you don't need a divergence sum. It's a finite sum. All you need is a sum is big enough, bigger than some fixed constant for every k. And 27 is just the quasi-independence on average condition, all with this restricted range Sk, and then without using a 0-1 law, because we know it doesn't exist in the inhomogeneous case. We're able to conclude that this set, well, again, it's got to be gamma in here, right? We're talking about the inhomogeneous problem, right? And this is it, right? So you can also ask whether condition M1 is the right one, or whether you can relax it in any way. Well, indeed, you can. You can, instead of M1, you can ask M1 on average. And this is another version of the Borel-Cantelli lemma in the same series of results, which has no relevance to the inhomogeneous Duffin-Schaeffer conjecture. We don't need such a relaxation of condition M1, because M1 simply is easy to verify. In the case of Duffin-Schaeffer, but nevertheless, there may be there may be a problem where you would need some flexibility. So you could replace M1, which basically is what's written here, but without this sums, right? So you can do the same with averaging. The downside is, in that case, you need to make sure that these sums, which earlier appeared to be just bigger than a constant, you need to be able to make them arbitrarily small, not just bigger than a constant. This seems like an extra condition, the requirement that you need to be able to make them arbitrarily small, but and in particular, it requires that the sequence En is in some way fine, in the sense that the measures of En tend to 0, at least over integers line in these sets AK. But in fact, if the sequence is not fine in that sense, if you have in your sequence sets which have infinitely many sets which measure is bounded below by a fixed constant, then everything actually is quite simple, and we've got this we've got this theorem where okay, I've provided here two statements, but perhaps you can it's probably actually well known anyway. So if the sequence of events has some subsequence of events has some level on their measure, then assuming property M1, you always have a full measure of the lim subsets, and you've got the same statement when you oh, I've written this way, but anyway, so the upshot is if in your sequence you've got a sequence, a subsequence, so that subsequence will arise from this condition on the lim subset, on the lim sup of measures, so that the measures are bounded below by a constant and property 1 holds and the measure is full, right? And this is a slightly sharper version of the first one. So you actually specify a set on which the measures are bounded below by a constant, right? And then in that case, you only require M1 on that specific subsequence. You don't need to hold it on the whole sequence. Right. One more remark. M1, which is repeated here, is a condition where you estimate the measure of En intersecting a set A like this. So in general, if you don't think of a Duffin-Schaeffer conjecture, but just of a Borel-Cantelli lemma, this may seem like sometimes an awful task to do, because the makeup of A might not be so easy, like in the Duffin-Schaeffer conjecture. But if you have some more structure, for example, if your probability space is defined on a subprobable metric space, and the probability measure is regular and doubling, then you can actually simplify it, and it's only necessary to check it for A being a ball. Right. I'm not sure how much more time I've got. Probably 5 or 10 minutes. Right. So for the rest of the talk, I'll just give you a few statements where I basically specialize the Borel-Cantelli lemmas I've shown before to what they would look like if you work in a dynamical system setting. So the setup is as follows: you've got a probability space X a mu, a measure preserving transformation T on X. You've got a sequence of measurable subsets, which we will call convergent or divergent if the sum of measures converges or diverges. So we'll be interested in the measure of this lim subset of t to the minus 1 an. So that's the set of X for which the orbit of X under T visits an. So if an was just a fixed set, then it would be about that orbit visiting a fixed set infinitely often, revisiting. So obviously this lim subset is of measure 0 if your sequence is convergent. This is a simple consequence of the first Borel-Cantelli lemma, and we'll call an a Borel-Cantelli sequence or BC sequence if this set, this lim subset, has measure 1, and obviously this is true only if the sequence is divergent. Right. So this is kind of standard terminology. I just recalled it, if we want to restate the Borel-Cantelli lemmas I've shown before, in this setting, our events are going to be basically this t to the minus n of an, right? And we need to interpret the various conditions that appear in those lemmas appropriately, and this is what we've got. That's one of the statements. So I recall here n1, which is the additional condition in the divergence Borel-Cantelli lemma we impose. As I said before, we set en to be t to the minus 1 of an. And just to sort of simplify, instead of asking n1, I'll ask a condition. I'll put this condition onto the actual dynamical system rather than the sequence an. Of course, this is going to be a little stronger than n1, but at least it makes it independent from your given sequence. But essentially, it's m1 in some written in some uniform form. So you're asking that this inequality holds for any measurable set A and any measurable set B, and epsilon n here is a sequence that tends to 0, and it has to be, that's the key here. This is where some uniformity comes in. It has to be independent of set B, right? So if you have a measure preserving system as before, satisfying Q1, then any divergent sequence an, which satisfies this condition 35, and it's basically what you get when you substitute this kind of events into the causing dependence condition on average in the Borel-Cantelli lemma, and use the fact that T is measure preserving, so you'll get this simplified property. So it's along the lines of 34, but here you've got some room because you don't need that kind of precision as in 34, but on the other hand, you need some kind of uniformity in terms of AM. Right, so the conclusion is that any sequence like that will be a Borel-Cantelli sequence, which means that the lim subset of these sets t to the minus n of an is of full measure. I probably will make a comment on condition U1. You can actually find something quite similar in the literature. So first I will compare it with assuming that the system is mixing. Mixing means that for every AB measurable sets, this limit of A intersection T to the minus M B equals mu of A, mu of B. And of course, 36 will imply the inequality that is stated in 37, right? For every A and B, you will have this inequality with some epsilon n, but the standard mixing assumption will make this sequence epsilon n dependent on both A and B, right? So mixing has equation, we only need inequality. But in condition U1, you need some uniformity on epsilon n in the sense that it should be independent of B. Right, so that's the whole point of this condition. You can always also find some more stringent requirements. So this is what you can find in several papers on quantitative recurrence. I've listed two in here. One is very recent, a few months old paper by Klumbach and Shah. Another one is a little older, where they also impose a condition like 37. I'm saying like because it's not precisely. They require here essentially equation with some remainder term, and they call it uniform mixing, and the requirement is that the arising sequence epsilon n is independent of both A and B, and the sequence itself is summable. So this is just to place this condition U1 into the perspective of what is there in dynamical systems, so you can decide yourself how feasible this condition is to verify. Right. You can of course specify that statement to the case when you have a metric space and your sequence of events is a sequence of shrinking balls. So what we have here is what people usually call a shrinking target problem. And then if you work in a sufficiently good metric space, then that condition U1 I've shown you before can be simplified by replacing arbitrary measurable sets A and B with arbitrary balls A and B. Right, so assuming this condition S1, you again have this equivalent of the Borel-Cantelli lemma I've shown you before. It's basically what you've seen with the only difference that the sets A and L are very specific, the balls, and condition S1 is a little simplified. And of course, you can make further simplifications if you assume, for instance, that mu is delta alphas regular. The sum of measures of A can be specified more precisely. Here is another, no, that's getting probably too fast. Another version of the Borel-Cantelli lemma specified the other version of the Borel-Cantelli lemma where you have condition M1. So this time it's specified to the case of a dynamical system, and the equivalent of M1 would be this condition, M2 will be this condition U2. Right, again, 41 is just the quasi-independence and average condition. I can see on my clock that the time is running out, so maybe really quickly, so some other consequences of those Borel-Cantelli lemma results, which are probably very well known anyway. So this is, if you like, an equivalent statement for the measure preserving system to be weak mixing. So typically in a definition, you would see averaging of these differences, but this is an equivalent formulation of weakly mixing. You need to take that limit like in mixing, but you need to exclude a set of zero density of n's. So in fact, it is equivalent to asking that limit, well, may not exist, just lim sup, and it's bounded above rather than equal. And two more, again, it's just all coming about from those Borel-Cantelli Lemmas I've stated, and some other auxiliary facts that already were known. So if you have a condition like this, where the lim inf, so in the previous statement, the limit was taken over essentially all n, you exclude only a set of zero density. This time you may exclude arbitrarily large set, so you're taking lim inf. If lim inf like that is bounded by mu a times mu b, then the system is ergodic. Typically, when you define ergodic, you would look at the intersection and some lower bound on that intersection. And that's the last one is a Borel-Cantelli lemma version of Borel-Cantelli lemma for a dynamical system when you have a sequence of events where the measures don't tend to zero. So when the lim subset is bigger, the measure is bigger than zero. Right, I think I'm done. Thank you very much for your attention. Hopefully it wasn't too fast.
Any questions? I'd request you to use the mic if you have any question.
Yeah. Hello, Victor. It's do you have counterexamples like in the Duffin-Schaeffer counterexamples for inhomogeneous approximation?
Yeah, well, I don't, but there is a paper by Ramirez where he gives some counterexamples. Yeah, so if you don't assume any sort of coprimality condition, then you would again get a counterexample. I'm just trying to find that. It may be up to a debate what sort of coprimality condition you need to impose, because in the classical case, the homogeneous case, the meaning of coprimality is very specific. You want to identify a rational fraction exactly. And that's why you ask A and N are coprime. So you don't repeat the same rational points in your sequence again and again, because this is where the counterexample of Duffin-Schaeffer comes from. So Ramirez constructed similar counterexamples in the inhomogeneous case.
Thank you.
Any more questions?
Hi, Victor. So
Hi.
some versions of the Borel-Cantelli lemma actually count the number of solutions, right? So
Yeah, I know. It's called strong Borel or whatever. Yeah.
So do you also have that? Can you count the number of solutions?
No. No.
What about Maynard-Kokoulopoulos? Do they also count it, or is it just?
No, there is. No, they prove just measure a result, but there is a more recent paper by other people, I guess just last year or even this year, where they give an asymptotic.
Okay, all right, thanks.
Any more questions? Okay, if not, then let's thank the speaker again.